Our story begins in the silent, star-strewn darkness between suns, an impossibly vast emptiness known as interstellar space. For billions of years, our solar system has traced its path through the galaxy, a self-contained island of planets and comets bound by the gravity of a single star. Anything that wanders in from the outside is an event of profound significance, a messenger from a distant and unknown shore. When the first of these travelers was spotted, a strange, elongated object that tumbled end over end, speculation ran wild. Was it merely an odd space rock? Or was it something more? Was it an artifact, a piece of alien technology, a spacecraft from a civilization we have yet to meet? It's a question that ignites the imagination, and it makes you wonder what else is drifting in the dark between the stars. We'd love to hear where you are pondering these questions and what time it is for you. So please leave a comment to let us know. And if you'd like to be notified of future stories from the cosmos, make sure you subscribe. That first visitor prepared us to look for more, to anticipate that our cosmic isolation was not as absolute as we once believed. So when another faint speck of light appeared, moving in a way that defied an origin within our own solar system, the scientific world held its breath. This new object was initially unassuming, a barely there smudge on a digital image, but it was traveling on a trajectory that was undeniably alien, a path that began countless millennia ago, in the gravitational embrace of another star, far, far away. That faint smudge of light was captured not by a lone astronomer patiently peering through an eyepiece, but by a tireless, robotic sentinel whose gaze sweeps across the heavens with methodical precision. This silent guardian is the Asteroid Terrestrial Impact Last Alert System, a name that perfectly encapsulates its solemn duty. Known simply as Atlas, it was conceived and built for a single, sobering purpose: to be our planetary tripwire, our last line of defense against a catastrophic impact from space. It is a system designed to find wandering asteroids and comets, specifically those whose orbits might one day intersect with Earth's, giving humanity a precious warning, perhaps weeks or only days, before a potential collision. The system's architects, led by astronomer John Tonry at the University of Hawaii, envisioned a cost-effective way to scan the entire visible sky, not just once in a while, but several times every single night. To achieve this, they built a network of telescopes, with the first two, the pioneers of the project, placed in one of the world's most pristine locations for astronomical observation: the Hawaiian Islands. One telescope sits high atop the dormant volcano Haleakala on the island of Maui, its white dome a stark feature against the rust-colored, otherworldly landscape. It stands at an altitude of over 3,000 meters, or nearly 10,000 feet, lifting it above the thickest, most turbulent layers of Earth's atmosphere. Its twin rests on the sweeping, barren slopes of Mauna Loa on the Big Island of Hawaii, another colossal shield volcano whose peak also pierces the upper atmosphere. In these remote locations, far from the light pollution of major cities, the air is thin, dry, and exceptionally stable, offering a crystal-clear window into the cosmos. These are not grand, monolithic instruments like the famous Keck Observatory nearby. The Atlas telescopes are comparatively modest. They are what is known as Schmidt telescopes, a special design optimized not for peering deeply into a tiny patch of sky to magnify a distant galaxy, but for capturing a vast panorama in a single shot. Each telescope has a primary mirror just half a meter, or a little under 20 inches, across. While that may sound small, their genius lies in their field of view. A single image from an Atlas telescope covers a staggering 7 degrees of the sky, an area so vast you could fit 140 full moons within its frame. Paired with a camera containing 110 million pixels, each of these robotic observatories can photograph a quarter of the entire night sky 4 times over the course of a single clear night, a feat unimaginable for traditional telescopes. Their operation is a relentless, automated ballet. As dusk settles over the Pacific, the dome shutters slide open, and the telescopes begin their pre-programmed survey, methodically marching across the celestial sphere, taking an exposure of 30 seconds before moving to the next patch of sky. In one night, they generate an immense river of data, terabytes of information flowing from the mountaintops to a data processing center. It is here that the true magic of the Atlas system happens. Sophisticated software meticulously compares the images. It digitally stacks the 4 pictures of the same sky region taken throughout the night, and then subtracts them from one another. Any star, galaxy, or nebula fixed and unmoving from our perspective vanishes in this subtraction, leaving behind only the things that have shifted their position against the stellar background. These movers are the quarry, the asteroids and comets of our solar system, silently orbiting the sun. Any detection is flagged and added to a list for human verification. And so it was on the night of December 28th, 2019. The Mauna Loa telescope, designated Atlas MLO, was performing its nightly duty when it captured a series of images containing an incredibly faint point of light, far too dim for the human eye to see, located in the constellation of Ursa Major, the Great Bear. The object was moving, but it was otherwise unremarkable, just another of the hundreds of potential near-Earth objects the system flags on a typical night. The data was relayed to the Minor Planet Center, the global clearinghouse located in Massachusetts, responsible for collecting and disseminating information about all small bodies in the solar system. The object was given a provisional name, a standard, almost bureaucratic designation, C2019Y4. This alphanumeric code is a compact story in itself. The C indicated that the object was believed to be a comet and that it was on a long period, or possibly non-periodic, orbit. The 2019 was the year of its discovery. The Y signifies the half-month in which it was found, in this case the second half of December, and the number 4 meant it was the fourth such object discovered in that specific period. And, as is tradition, the name of the discoverer was appended, so it became C 2019 Y4, Atlas. At first, this was just one more entry in an ever-growing catalog. But as other observatories around the world were alerted and began to train their own instruments on this faint speck, a trickle of new data points began to flow back to the Minor Planet Center. With each new observation, astronomers could refine their understanding of the object's path through space. And as they plotted its trajectory, a startling picture began to emerge. The path was not the familiar closed ellipse of an asteroid or comet belonging to our solar system, a path that would inevitably loop back around the sun. Instead, this object was moving on a different kind of curve entirely, an open-ended, hyperbolic trajectory. This meant it was not bound by our sun's gravity. It was a tourist, a traveler, just passing through. It had fallen towards our solar system from the vast emptiness of interstellar space, and after a brief, fiery encounter with our star, it was destined to be flung back out into that same darkness, never to return. The Atlas system, a shield built to watch for threats from within our own cosmic neighborhood, had inadvertently spotted an intruder from an unimaginable distance, a true alien in our midst. The discovery was a moment of profound serendipity, a testament to the fact that when we observe the universe with an open and persistent gaze, we are bound to find things we were not even looking for. The quiet, robotic sentinel on the slopes of a Hawaiian volcano had done more than its duty. It had found a messenger from the stars. Now, the urgent task for the world's astronomers was to study this visitor as intensely as they could during its fleeting passage, to wring every possible secret from its ancient heart before it disappeared forever. The global astronomical community, now buzzing with the news, scrambled to turn its collective eyes toward this faint traveler. The coordinates of CIS 2019 Y4 were distributed worldwide, and in observatories from the arid deserts of Chile to the volcanic peaks of the Canary Islands, telescopes large and small slewed into position, their sensors ready to catch the precious few photons of light arriving from this enigmatic guest. In these early days, the object remained visually unimpressive, little more than a ghostly, fuzzy patch against the velvet black of deep space. But every new data point, every precise measurement of its position, was a crucial piece of a grand celestial puzzle. The initial task was to confirm the object's path beyond any shadow of a doubt. The preliminary orbit, calculated from the first few Atlas observations, was tantalizingly ambiguous. It was what astronomers call a nearly parabolic orbit, a path so elongated, so stretched out, that it was nearly impossible to tell if it was a closed loop or an open-ended trajectory. Imagine throwing a stone into the sky. If you throw it gently, it follows a simple arc, an ellipse, and falls back to Earth. If you could throw it with incredible force, just enough to counteract Earth's gravity, it would theoretically trace a parabola, escaping to infinity, but with its speed eventually dropping towards zero. But if you were to fire it from a cannon, giving it energy to spare, it would fly away on a hyperbola, forever escaping Earth's pull and retaining a significant velocity even at a great distance. The path of C2019Y4 was balanced on a knife's edge between the last two possibilities. The mathematical value that describes the shape of an orbit is called its eccentricity. A perfect circle has an eccentricity of 0. A gentle ellipse is somewhere between 0 and 1, and the escape velocity parabola has an eccentricity of exactly 1. An interstellar traveler, a true outsider, must have an eccentricity greater than 1. The initial calculations for C2019Y4 placed its eccentricity excruciatingly close to that magic number. So close that the difference could have been a simple measurement error. This sparked a quiet but intense debate among astronomers. Was this object the long-awaited third interstellar visitor, a successor to the mysteries of Oumuamua and Borisov? Or was it something else, a native of our solar system, but one hailing from its most distant and enigmatic realm? This realm is known as the Oort cloud, a concept first proposed by the Dutch astronomer Jan Oort in the mid-20th century. He theorized that our solar system was not just the Sun and its planets, but that it was encased in a colossal spherical shell of icy bodies, a cosmic debris field of trillions of comets. This cloud is unimaginably vast, beginning perhaps a few thousand times farther from the Sun than the Earth, and extending almost a light year into space, nearly halfway to our nearest stellar neighbor, Proxima Centauri. These are the pristine, deep-frozen leftovers from the formation of the solar system some 4.6 billion years ago. Most of them will orbit there in the dark for eternity. But occasionally, the gentle gravitational nudge of a passing star or the tidal forces of our own Milky Way galaxy can disturb one of these sleeping comets, sending it on a slow, multi-million-year fall toward the inner solar system. For a comet making this epic journey for the very first time, its orbit would be a vast, stretched ellipse, so extreme that its eccentricity would be incredibly close to 1, making it appear, for all intents and purposes, parabolic. For days, the data was too sparse to make a definitive call. But as more observatories contributed their measurements, the path was refined with increasing precision. Each new observation chipped away at the uncertainty, narrowing the possibilities. Finally, the verdict came in. With a high degree of confidence, the astronomical community concluded that the eccentricity was just shy of 1. C-2019Y4 was not an interstellar object. It was, instead, a new long-period comet, a primordial member of our own solar system, making its very first voyage inward from the staggering depths of the Oort cloud. Its journey had begun hundreds of thousands, perhaps millions of years ago, from a region of space so cold and distant that the sun would appear as little more than an unusually bright star. Calculations suggested its aphelion, its farthest point from the sun, was at a distance of roughly 50,000 astronomical units, which is 50,000 times the distance from the Earth to the sun. That is a journey of some 7.5 trillion kilometers, or nearly 4.7 trillion miles. Though it wasn't the alien visitor some had hoped for, the comet was still an object of immense interest. As a first-time visitor from this pristine, frozen repository, it was a time capsule, carrying with it the unaltered chemical ingredients that formed our solar system billions of years ago. And it was already beginning to put on a show. As it journeyed from beyond the orbit of Jupiter towards the orbit of Mars, it began to brighten at a truly astonishing rate. Comets are often compared to dirty snowballs, amalgams of frozen water, ammonia, methane, and carbon dioxide, all mixed with dust and rock. As they approach the sun, the increasing solar radiation heats their surfaces. These ices do not melt. In the vacuum of space, they sublimate, turning directly from a solid into a gas. This outgassing creates a vast, fuzzy cloud around the comet's solid core, or nucleus. This cloud is called the coma, and it can swell to be larger than planets. The coma of C-2019Y4 was already estimated to be enormous, perhaps 160,000 kilometers, or nearly 100,000 miles, in diameter. Spectroscopic analysis of the light from this coma revealed a distinct greenish glow, the signature of diatomic carbon and cyanogen, common molecules in comets that fluoresce under the bombardment of ultraviolet sunlight. What was truly exciting, however, was its dramatic increase in brightness. Its light output was doubling every few days. Extrapolating this trend forward, astronomers made a bold prediction. By the time the comet reached its perihelion, its closest approach to the sun in May of 2020, it could become brilliantly bright, perhaps as bright as the planet Venus in the night sky. It might even become visible during the daytime. The world was hungry for a celestial spectacle, and C-2019Y4 Atlas seemed poised to become a great comet, a once-in-a-generation event that would blaze across our skies. The stage was set for a magnificent performance from this ancient traveler, a fiery welcome after its long, cold journey. No one could have possibly predicted that this rising star was destined not for a blaze of glory, but for a sudden and violent self-destruction before it even reached its closest approach to the sun. The first hint that something was amiss came not as a sudden cataclysm, but as a quiet faltering. Throughout February and into early March of 2020, the astronomical community, both professional and amateur, watched with growing excitement as Comet Atlas continued its magnificent brightening, precisely on schedule. Its light curve, a graph plotting its brightness over time, was a steep, promising incline. Enthusiasts and sky watchers in the northern hemisphere were preparing their binoculars and telescopes for what was hoped to be the celestial event of the decade. But then, in the third week of March, the incline flattened. The comet, which had been so reliably and rapidly increasing its luminosity, simply stopped getting brighter. At first, this was dismissed as a temporary lull, a common enough occurrence in the unpredictable lives of comets as different patches of ice and dust on their rotating surfaces are exposed to the sun. Perhaps a less active region had turned towards the sunlight, momentarily throttling down its gaseous output. But the lull persisted. Days turned into a week, and then another. And still, the comet stubbornly refused to brighten. Then, the data took a more alarming turn. It began to fade. This was a deeply worrying sign. A comet on an inward trajectory, flying closer to the immense furnace of the sun with every passing second, should be doing the exact opposite. Its activity should have been ramping up exponentially, its coma swelling, and its tail unfurling spectacularly. For it to be fading could mean only one thing. The engine at its heart, the solid nucleus, was in trouble. The process of sublimation that was driving its brilliant display was sputtering out. The first visual evidence that this was more than just a temporary pause came from the dedicated community of amateur astronomers, whose countless hours at the eyepiece often allow them to spot subtle changes before major observatories can retrain their scheduled instruments. On the 2nd of April, an amateur astronomer named José de Queiroz, imaging the comet from Portugal with his own backyard telescope, captured a striking image. Where there had been a relatively sharp, star-like central condensation within the fuzzy coma, there was now an elongated, almost cigar-shaped smudge. It was a clear indication that the nucleus was no longer a single, solid body. It had begun to come apart. This news sent a ripple through the astronomical world, and professional observatories quickly followed up. Using more powerful instruments, they confirmed Queiroz's observation. The comet's core was indeed stretched, a definitive sign of catastrophic fragmentation. The great comet that was promised was now a dying one, disintegrating before the world's eyes. While a disappointment for the public, this event presented a rare and invaluable opportunity for scientists. A comet's nucleus is usually shrouded from view, hidden deep within the bright, dense coma. Witnessing one break apart was like being given a chance to perform a remote autopsy, to peer into the primordial heart of a visitor from the Oort cloud. To get the clearest possible view, astronomers turned to the most powerful optical instrument available, the Hubble Space Telescope. Orbiting high above the distorting blanket of Earth's atmosphere, some 540 kilometers, or 335 miles. Overhead, Hubble's 2.4-meter, or nearly 95-inch mirror, can achieve a resolution that ground-based telescopes can only dream of. On April 20th, Hubble focused its sharp eye on the fading ghost of Comet Atlas. The images it returned were breathtaking and unequivocal. The elongated smudge seen from the ground was resolved into a beautiful, tragic string of icy pearls. Hubble could distinguish at least 30 separate fragments, each a brilliant shard of the original nucleus, trailing one another like ducks in a row. A few days later, on April 23rd, it looked again. The view had changed. Some of the fragments had vanished, likely having disintegrated into clouds of dust too fine to see, while others had visibly dimmed. The two main leading pieces were separated by a distance of about 3,860 kilometers, or roughly 2,400 miles, approximately the distance between London and New York. The comet was not just broken. It was actively falling apart, piece by piece, as it raced towards the sun at a velocity exceeding 160,000 kilometers per hour, or 100,000 miles per hour. The question now was why? Why had this particular comet, after a journey of millions of years through the frozen void, failed so spectacularly at the final hurdle? The answer lies in the violent transition from the unimaginable cold of the outer solar system to the searing heat of the inner solar system. For eons, the nucleus of Comet Atlas had existed in a state of near-perfect preservation, at temperatures hovering just a few tens of degrees above absolute zero, colder than minus 200 degrees Celsius, or minus 330 degrees Fahrenheit. It was a fragile object, likely not a solid, monolithic rock, but a loose agglomeration of ices and dust, held together by its own feeble gravity, and the frozen volatiles acting as a weak cement. As it fell sunward, the gentle warmth began to penetrate its surface. This created immense thermal stress. The sunlit side of the nucleus would heat up rapidly, while its dark side remained cryogenically frozen. This vast temperature difference across its body would cause the material to expand and contract unevenly, creating deep fissures and cracks, much like a glass of ice water cracking when hot water is poured into it. Furthermore, as the ices sublimated, they didn't just passively evaporate. They burst forth in powerful, concentrated jets from these cracks and vents on the surface. If the nucleus was rotating, as most celestial bodies are, these jets could act like erratic rocket engines. If they were not perfectly aligned with the comet's center of mass. They could impart a torque, causing the nucleus to spin faster and faster. As the rotational speed increased, centrifugal forces would begin to tear the fragile body apart from within. It's a delicate balance. A stronger, more consolidated nucleus might survive this process, but Comet Atlas was likely what astronomers refer to as a rubble pile, a loosely bound collection of smaller pieces. The increasing spin was simply too much for its weak internal cohesion to handle. It reached a rotational speed where the outward fling of centrifugal force overwhelmed the inward pull of its own gravity, and it simply flew apart. Analysis of the fragments by Hubble suggested that the original nucleus might have been surprisingly small, perhaps no more than the length of 2 American football fields. An object so tiny, making such a monumental journey, was always living on borrowed time. The dream of a great comet visible to the naked eye had dissolved into a ghostly trail of cosmic dust. But in its place, astronomers were given a fleeting, unprecedented glimpse into the life and death of a primordial wanderer from the dawn of our solar system. The dramatic self-destruction of Comet Atlas, while a spectacle, was ultimately a story that belonged to our own solar family. Its fragile composition spoke of the conditions in the ancient Oort cloud, a puzzle solved with the familiar tools of cometary science. But just a couple of years earlier, the heavens had sent us a mystery of a completely different order, an enigma that defied all our familiar categories and stretched the very definition of what a natural object could be. The stage for the intense scrutiny of any unusual object had been set by a visitor that was far stranger, and one whose true nature remains a subject of fierce debate to this day. Its story begins on October 19th, 2017, not with the Atlas survey, but with its older, more powerful sibling, another sentinel keeping watch from the summit of Haleakala in Hawaii. This was the Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS. It is a more substantial instrument, with a 1.8 meter, or roughly 71-inch, primary mirror and a camera boasting an incredible 1.4 billion pixels. Its mission is the same as Atlas's: to find moving objects against the background of stars. On that night, an astronomer named Robert Warwick was reviewing the system's latest detections when he flagged a faint point of light. It was moving fast, very fast. But what truly set it apart was its trajectory. When astronomers plotted its path, they found it was not just hyperbolic. It was radically hyperbolic. Its eccentricity was calculated to be approximately 1.2. This was not a subtle statistical anomaly that could be chalked up to measurement error. It was a screeching celestial siren announcing that this object was not, under any circumstances, from our solar system. It had come from the direction of the star Vega in the constellation Lyra, a journey that, even at its blistering speed, must have taken hundreds of thousands of years. It was the first time in human history that an object from another star system had been definitively identified passing through our own. It was given the designation 1I 2017 U1, the I standing for interstellar. But it also received a more fitting name from its Hawaiian discoverers. Oumuamua, a word that means a messenger from afar arriving first, or scout. As this interstellar scout looped around the sun and began its journey back out into the void, astronomers raced to study it with every telescope they could bring to bear. And the more they looked, the stranger Oumuamua became. Firstly, it showed no signs of being a comet. As it whipped around the sun at a close approach of about 37 million kilometers, or 23 million miles, it should have been heated intensely, causing any surface ices to sublimate violently and form a bright coma and tail. Yet it displayed none. It was completely inert, appearing as a sharp, star-like point of light. This suggested it was an asteroid, a dry piece of rock and metal. But that raised its own set of problems. How could a rocky object survive such an immense journey between stars without being eroded to dust by cosmic rays and interstellar gas? And what kind of star system would eject a purely rocky body with such force? Then came the analysis of its light. As astronomers watched Oumuamua, they noticed its brightness was varying wildly by a factor of 10 over a period of about 8 hours. This meant the object was tumbling, and as it tumbled, it was presenting a radically different profile to our telescopes. To explain such a dramatic change in brightness, the object had to have a truly extreme shape, unlike any known asteroid or comet in our solar system. The most popular models suggested it was shaped like a cigar, perhaps 10 times as long as it was wide, maybe 400 meters or a quarter of a mile, in length, but only 40 meters or 130 feet, thick. Other models suggested it might be a flat, pancake-like shard. Either way, it was a celestial anomaly. No natural process that we understood could readily explain the formation of such an object. But the greatest mystery was yet to come. As astronomers tracked Oumuamua's departure with exquisite precision, they noticed something that defied the laws of gravity. After swinging past the sun, it began to speed up. It was a tiny acceleration, but it was unmistakable and persistent. The object was being gently pushed away from the sun by some unseen force. This phenomenon, known as non-gravitational acceleration, is well understood in comets. The outgassing of jets of gas and dust from the sunlit side of a comet's nucleus acts like a cluster of small rocket engines, giving the comet a push. But Oumuamua had no visible jets. It had no coma. It was a ghost rocket, exhibiting the effects of propulsion with no visible means of propulsion. This central contradiction left the scientific community baffled and divided. Explanations were put forth, all of them exotic. Perhaps it was made of some unusual material, like solid hydrogen, that would sublimate invisibly. But such an object would be incredibly fragile and unlikely to survive its journey. Perhaps it was an object of immense porosity, a cosmic dust bunny so fluffy that the pressure of sunlight alone could push it. Then came the most sensational hypothesis, championed by the then chair of Harvard's astronomy department, Avi Loeb. He argued that if the push was coming from the pressure of sunlight and the object was not a fluffy dust ball, then it must have a very large surface area and be incredibly thin. In other words, it had the characteristics of a solar sail. He posited that Oumuamua could be an artifact of an extraterrestrial civilization, a piece of derelict technology, a probe, or the discarded sail from an alien starship, tumbling through our solar system. The suggestion was met with immense skepticism from the majority of the scientific community, but it captured the public's imagination and highlighted just how little we understood this visitor. By the time this acceleration was confirmed, Oumuamua was already too far away and too faint for even the most powerful telescopes to observe. It had slipped back into the darkness, leaving a trail of profound questions in its wake. This encounter with the genuinely bizarre and unexplainable nature of Oumuamua fundamentally reshaped the search for interstellar objects. It proved they existed and demonstrated that they could defy our neat classifications. It primed astronomers to expect the unexpected. So, when C2019Y4 Atlas was discovered, the memory of Oumuamua was fresh in everyone's mind. The initial hyperbolic trajectory of Atlas immediately raised the question: had another scout arrived? Was this another messenger from the stars, offering a new set of clues about the galaxy beyond our home? The experience with Oumuamua had honed the world's astronomical reflexes, making the entire system of observation and analysis faster and more efficient, ready to pounce on the next visitor the moment it was spotted. And so, with reflexes sharpened by the strange passage of Oumuamua, the world sky surveys continued their nightly vigil, now more alert than ever to the possibility of another guest from the interstellar dark. The dramatic saga of Comet C2019Y4 Atlas, the fragile visitor from our own Oort cloud that had promised a spectacular show only to disintegrate, served as a valuable, if disappointing, dress rehearsal. It proved how quickly a new object could be found, tracked, and analyzed by a global network of telescopes. The Atlas system itself, having added this fascinating footnote to cometary science, went back to its primary task, its robotic eyes sweeping the sky night after night, searching for the next faint wanderer. For almost 3 years, the cosmos remained quiet. Then, on the 7th of January, in the year 2023, the system once again flagged a new object. This time, The detection came from the Atlas telescope located at the Sutherland Observing Station in South Africa, a testament to the survey's expanding global reach. It was an exceptionally faint object, a mere pinprick of light in the constellation of Tucana, the Toucan. Following protocol, it was given a provisional designation, a 2023A3. The A, in this case, stood for asteroid, as the tiny object showed no visible signs of a coma or tail. It appeared, for all intents and purposes, to be a solid, inert rock. But when the first orbital calculations were made, they revealed something truly extraordinary. There was no ambiguity this time, no knife-edge calculation hovering around an eccentricity of 1. This object's path was wildly, unambiguously hyperbolic, with an eccentricity of approximately 2.3. It was moving with an astonishing velocity, having entered our solar system at a speed of around 30 kilometers per second, or nearly 67,000 miles per hour, relative to the Sun. This was not a drifter from the Oort cloud. This was a celestial cannonball fired from the depths of interstellar space. The discovery was quickly confirmed, and the object was officially redesignated as the third known interstellar visitor, receiving the formal name 3I Atlas. The 3I was a historic marker, signifying it as the third interstellar object ever detected, following the enigmatic Oumuamua and the more conventionally cometary Borisov. Yet, as astronomers began to study 3I Atlas more intensely, it started to defy this simple classification. As it drew closer to the Sun, it began to change. Faintly, almost imperceptibly at first, it started to grow a fuzzy halo, a coma. Shortly thereafter, a delicate, wispy tail began to trail behind it. This was classic cometary behavior, driven by the sublimation of ice from its surface. This activity prompted another redesignation, this time from an interstellar asteroid to an interstellar comet. On the surface, the mystery seemed solved. Oumuamua was the strange, inert, rocky object. Borisov was a more or less normal interstellar comet. And now 3I Atlas appeared to be a second example of an interstellar comet. But science thrives on details, and the details of 3I Atlas weren't adding up. It was a comet, yes, but it was a deeply peculiar one. Its activity level was perplexingly low. Given its trajectory, which would bring it to a perihelion, or closest approach to the Sun, of about 1.8 astronomical units, 1.8 times the Earth-Sun distance, placing it just inside the orbit of Mars, it should have been outgassing far more vigorously. A typical comet made of water ice, even a small one, would be expected to produce a much more brilliant coma and a more substantial tail when exposed to that level of solar radiation. The visitor was active, but only just barely. It was as if its engine was sputtering, running on a fuel source that was either almost depleted or fundamentally different from what we are used to. This was the central puzzle of 3I Atlas. It wasn't a comet that wasn't a comet, like Oumuamua, which showed no cometary features at all while still accelerating. Instead, 3I Atlas was a comet that wasn't acting like one. It presented a frustrating middle ground. It had just enough cometary activity to earn the name, but not enough to be explained by our standard models of comets from our own solar system. Its very existence seemed to be a contradiction. Spectroscopic analysis, which breaks down the light from an object to determine its chemical composition, only deepened the mystery. While the data was difficult to obtain from such a faint object, initial results suggested that the gas in its coma was unusually rich in carbon monoxide and carbon dioxide, but deficient in the water vapor. That dominates the activity of most comets we know. This chemical fingerprint was another clue that this visitor was born in a very different environment from our own solar systems. Comets. The alien speculation that had ignited around Oumuamua began to whisper once more, albeit in a more subdued form. Could this be another artifact? Perhaps an older, more derelict one, venting the last vestiges of some unknown propellant as it tumbled through our system? The presence of a coma and tail made a natural explanation far more likely. Yet the object's sluggishness and strange composition kept it firmly in the category of the deeply weird. It was a brand new kind of puzzle. Oumuamua was a mystery of omission. It lacked the coma it should have had. 3I Atlas was a mystery of character. The coma it did have was not the right kind. This interstellar guest was not shouting its secrets, but it was offering subtle, tantalizing clues that pointed towards a genesis story far from our own, forcing astronomers to reconsider the very nature of what a comet could be. This strange, underwhelming character of its coma was the central puzzle that occupied astronomers as 3I Atlas continued its silent fall toward the sun. Its sluggishness was a riddle, a whisper from the void that hinted at a composition fundamentally alien to our own solar system's building blocks. Often in astronomy, the most profound insights are not gleaned from a static, unchanging object, but from moments of dramatic transformation. A star that explodes as a supernova, an asteroid that collides with a planet, or a comet that performs an unexpected maneuver can reveal more in a few hours of observation than years of patient watching. And so it was with 3I Atlas. The celestial drama began in early February of 2023, as the interstellar object was closing in on its perihelion, its point of closest approach to the sun. Observers monitoring the faint smudge of light noticed a sudden and dramatic change. Over a period of just a few days, the comet brightened by a factor of more than 100. It was a spectacular outburst, a sudden flare that momentarily brought the object from the edge of visibility into the range of more modest professional telescopes. For a moment, it seemed as if the comet was finally waking up. Perhaps its journey had brought a previously shielded pocket of highly volatile ices to the surface, which, upon being exposed to the strengthening sunlight, began to sublimate with explosive force. This was the kind of behavior that, while dramatic, was not entirely without precedent in the cometary world. But the excitement was short-lived. The brilliant flare was not the beginning of a sustained period of activity. Instead, it was a death throe. Almost as quickly as it had brightened, 3I Atlas began to fade. And as it faded, its appearance changed in a fundamental way. The central condensation, the tiny star-like point of light that marked the location of the solid nucleus within the coma, grew soft and diffuse. It was the telltale sign of a nucleus in catastrophic distress, a visual echo of the fate that had befallen its namesake, the Oort cloud comet C 2019 Y4. The world's most powerful observatories were mobilized to get a closer look. The James Webb Space Telescope, with its unparalleled sensitivity to the infrared light that reveals the heat signatures and chemical compositions of cold, distant objects, performed crucial observations. Its data confirmed that the outburst had released a significant cloud of dust and gas, but it also saw that the central engine was gone. To get the sharpest possible visual picture, astronomers once again turned to the Hubble Space Telescope. Its vantage point above the blurring effects of the atmosphere allowed it to act as a celestial microscope. When Hubble focused on the fading ghost of 3I Atlas, it saw not one object, but two. The nucleus had split into two distinct pieces, which were slowly, almost lazily, drifting apart from one another. The comet had broken its heart. The cause of this sudden, violent end was intimately linked to the very properties that had made it so peculiar from the start. Its strange chemical composition, rich in supervolatile substances like carbon monoxide, meant that it was a fundamentally fragile object. Water ice, the primary ingredient of our solar system's comets, is a relatively sturdy building material. It sublimates at a fairly high temperature, meaning a comet has to get quite close to the sun before it becomes violently active. But carbon monoxide turns from a solid to a gas at a far, far lower temperature, just a few tens of degrees above absolute zero. Colder than minus 230 degrees Celsius, or minus 380 degrees Fahrenheit. An object held together by such a volatile glue is like a sculpture carved from dry ice. It is stable in the deep freeze of interstellar space, but bring it even into the relative warmth of the outer solar system, and it begins to fall apart. The outburst was likely the result of the sun's energy penetrating the surface and reaching a large reservoir of this frozen carbon monoxide. The resulting flash sublimation would have been powerful enough to crack the nucleus in two, a process that required remarkably little energy given the object's inherently weak structure. The two main fragments continued on their path, for a time appearing as a double comet, But even they were not long for this world. They continued to shed material, to fizzle and disintegrate until they were no longer detectable as solid objects, having dissolved into a faint, expanding cloud of dust and gas. The interstellar visitor had not survived its first and only encounter with our star. For the public, it was another celestial non-event, a faint object that briefly flared and then vanished. But for the scientists studying it, this act of self-destruction was the Rosetta Stone they had been waiting for. The comet's death was the ultimate clue to its life. Its inability to survive even the gentle warmth at the orbit of Mars was a definitive statement about its composition. It could not be a simple water ice comet that was for some reason underperforming. It had to be made of something far more volatile, something so fragile that its journey through our solar system was a suicidal one from the very beginning. The puzzle of its sluggish activity and its sudden demise were two sides of the same coin. It was sluggish because its activity was driven by these super volatiles, which did not produce a bright, water-rich coma. And it because the same super volatiles that drove its faint activity also made it structurally unsound, unable to withstand the stresses of its solar encounter. The visitor had immolated itself, but in its ashes, a new and elegant explanation for its origin and its bizarre behavior was about to take shape. An explanation that would connect this tiny interstellar fragment to the mysterious worlds orbiting distant stars. The final, fatal fragmentation of 3I Atlas was not an end to its story, but rather the beginning of its true understanding. In its violent dissolution, the interstellar visitor had offered up its deepest secrets, transforming from a mysterious point of light into a cosmic crime scene. For the scientists who had tracked its journey, the task now was to sift through the evidence left behind in the silent vacuum of space, to conduct an autopsy from a distance of hundreds of millions of kilometers. The clues were as clear as they were compelling. There was the object's extreme fragility, its inability to survive even the modest solar heating found near the orbit of Mars. There was its bizarre cometary activity, a coma and tail that were present but strangely anemic. And finally, there was the chemical fingerprint carried in its light, a composition that hinted at an abundance of super volatile ices like carbon monoxide. It was the job of theoretical astrophysicists to take these disparate clues and weave them into a coherent narrative, a life story that could explain not only the object's dramatic demise, but also its strange journey and its distant birth. The process began by eliminating the familiar. Could 3I Atlas simply be a water ice comet, like those from our own Oort cloud, that just happened to form around another star? The evidence screamed no. Our own solar system had already provided a perfect control subject in the form of the second interstellar visitor, 2I Borisov. Discovered in 2019, Borisov was a much more conventional comet. It was rich in water, produced a magnificent coma and tail as it neared the Sun, and survived its passage intact. It looked and behaved just like one of our own. 3I Atlas was its polar opposite. It fell apart at a distance from the Sun, where a water ice comet should have been just beginning its most spectacular activity. The water ice model simply did not fit the facts. The visitor was made of weaker stuff. The next possibility was to consider if it was a rocky, inert object like Oumuamua, whose own strange acceleration remains a profound puzzle. This too was a poor fit. Unlike Oumuamua, 3I Atlas was undeniably active. It clearly produced a coma and a tail, however faint. It was shedding mass, an activity that ultimately led to its own destruction. It was not a passive, tumbling rock. It was an active, outgassing body. With the standard models ruled out, scientists were forced to look for more exotic, though entirely natural, explanations. The key lay in its fragility and its super volatile composition. The question became, where in the universe do you find large bodies made primarily of materials like frozen nitrogen and carbon monoxide? The answer was not in some hypothetical, unknown environment, but in a place that was uncannily familiar. You find them in the cold, dark outer reaches of our own solar system. You find them in the Kuiper Belt, the vast disk of icy debris that lies beyond the orbit of Neptune. The undisputed king of this realm is Pluto, a world that stunned planetary scientists when the New Horizons spacecraft flew past it in 2015. The images revealed a geologically active world with vast, smooth plains of frozen nitrogen, majestic mountains of water ice-capped with methane snow, and a thin nitrogen atmosphere. Pluto and other large Kuiper Belt objects like Eris and Makemake are not dirty snowballs of water ice. They are complex worlds whose surfaces are dominated by these far more volatile ices, which exist in a delicate balance between solid, liquid, and gas, even at temperatures of minus 230 degrees Celsius, or minus 390 degrees Fahrenheit. This realization was the spark that ignited the leading hypothesis, a theory championed by astronomers Darrell Seligman and Alan Stern. They proposed that 3I Atlas was not a comet in the traditional sense at all. It was, instead, a nitrogen iceberg. They argued that the visitor was a fragment of a larger body, a piece of an exo-Pluto, a Pluto-like world orbiting a distant star. The story they pieced together was both epic and elegant. Imagine, hundreds of millions of years ago, in a star system light years from our own, a world much like Pluto orbits in the frigid twilight. This world has a crust made primarily of solid nitrogen. A violent event takes place. Perhaps another large body from that system's own Kuiper belt crashes into it, or a gravitational shove from a giant planet sends its moons colliding. This impact blasts a massive shard of the planet's nitrogen ice crust into an escape trajectory, flinging it out of its home star system and into the vast, lonely darkness of interstellar space. For countless millennia, this fragment drifts through the galactic void, perfectly preserved in the near absolute zero temperatures of deep space. It is a pristine piece of another world's surface. By sheer cosmic chance, its long, random walk through the galaxy brings it into the gravitational grasp of our own sun. As it begins its fall toward our inner solar system, the story of its strange behavior and eventual demise unfolds naturally. Even at the distance of Saturn's orbit, the faint warmth of the sun is enough to begin sublimating the incredibly volatile nitrogen ice. This process is slow and inefficient, creating the faint, sputtering coma that astronomers observed. A coma dominated not by water vapor, but by the nitrogen and carbon monoxide that made up the object's very substance. This also explains its fragility. A body made of nitrogen ice is inherently weak, far more so than one made of water ice. As the object drew closer to the sun, the warming created thermal stresses, and the outgassing created torques that spun the fragile body. It was a combination it could not withstand. The outburst was the moment the thermal stresses reached a breaking point, and the nucleus cracked, exposing a fresh surface of ice to the sun in a brilliant flash. The subsequent fragmentation was simply the rest of the iceberg crumbling under this gentle but relentless solar assault. The autopsy was complete, and the conclusion was as startling as it was beautiful. 3I Atlas was not a primordial comet. It was a piece of a planet. The faint smudge of light that had briefly graced our skies was a messenger carrying a fragment of the surface of an alien world, a world very much like the one that lies at the edge of our own solar system. This single, powerful idea that 3I Atlas was a planetary fragment acted like a master key, suddenly unlocking every puzzling aspect of the object's behavior. The collection of strange, disconnected observations that had baffled astronomers now snapped into place, forming a coherent and deeply satisfying picture. The hypothesis didn't just explain one mystery, it explained all of them. And it did so with a beautiful simplicity, using physics and geology that were already well understood from studying the worlds in our own cosmic backyard. Let's revisit the central riddle. The comet that was a comet, but wasn't acting like one. It had a coma and tail, but they were disappointingly faint. The nitrogen iceberg model resolves this contradiction perfectly. Nitrogen is what scientists call a super volatile ice. It turns from a solid directly into a gas at an incredibly low temperature, around minus 210 degrees Celsius, or roughly minus 350 degrees Fahrenheit. This means that a body made of nitrogen ice would begin to outgas or sublimate at an immense distance from the Sun, far beyond the orbit of Saturn, where the sunlight is almost too weak to have any effect on a traditional water-ice comet. This explains why 3I Atlas was active at all on its particular trajectory, which never brought it especially close to the Sun. But why was it so faint? The answer lies in the physics of sublimation. The amount of gas produced by a nitrogen iceberg at that distance is relatively small, and nitrogen gas itself is invisible. A comet's brightness comes primarily from sunlight, reflecting off the vast cloud of dust particles that are dragged away from the nucleus by the sublimating gas. For a fragment of a planetary surface, like a piece of Pluto's vast nitrogen glacier known as Sputnik Planitia, the composition would be almost pure frozen nitrogen, with very little dust mixed in. The sublimating gas, therefore, would not have much dust to carry with it, resulting in a thin, transparent coma that was difficult to see. It was a ghost comet, powered by a nearly invisible fuel. It was active, but not in a way that would produce a dazzling visual spectacle. The model had perfectly explained the object's sluggish character. Next was the question of its chemical composition. Early analysis of its light had pointed to a coma rich in carbon monoxide, but strangely lacking in water. This, too, aligns perfectly with what we see on Pluto. While Pluto's majestic mountains, some towering as high as 3,500 meters, or 11,000 feet, are made of rock-hard water ice, its vast plains and flowing glaciers are composed of a mixture of more volatile ices. The dominant ingredient is nitrogen, but it is laced with significant amounts of frozen carbon monoxide and methane. On Pluto, the water ice is so cold it acts as the planet's bedrock, an inert foundation upon which the more active geology of the nitrogen cycle plays out. If a massive impact were to strike Pluto, it wouldn't necessarily chip off a piece of the water ice mountains. It is far more likely to blast away a fragment of the more brittle, expansive nitrogen ice plains. Such a fragment would naturally be composed of exactly what was observed in 3I Atlas, a mixture of nitrogen and carbon monoxide, with very little water ice mixed in. The visitor's chemical fingerprint was not just consistent with a planetary fragment, it was a near-perfect match for the surface of a world like Pluto. The most dramatic piece of evidence, of course, was the object's catastrophic disintegration. Why did it fall apart so easily? Again, the nitrogen iceberg hypothesis provides a straightforward answer. Solid nitrogen is a notoriously weak material. It has very low tensile strength, meaning it doesn't take much force to pull it apart. Compared to the relative durability of water ice, a nitrogen iceberg is exceptionally fragile. As 3I Atlas journeyed closer to the Sun, it was subjected to a double assault. Firstly, The increasing solar radiation created immense thermal stress. The side facing the sun would warm up, causing the nitrogen to expand, while the side facing away remained cryogenically frozen in the cold of space. This temperature gradient would have created deep cracks and fissures throughout the object's structure. Secondly, the sublimation process itself was a source of destruction. As the nitrogen turned to gas, it would erupt in jets from these fissures. If the object was rotating, even slowly, these jets would act like tiny, misaligned thrusters, pushing on the object and causing it to spin faster and faster. The combination was lethal. The ever-increasing spin rate generated centrifugal forces that tried to tear the object apart from the inside, while the thermal stresses weakened its structure from the outside. A sturdy water-ice comet might have survived, but for a fragile nitrogen iceberg, it was a death sentence. The bright outburst was likely the moment the first major fracture occurred, and the subsequent fading and disappearance was the rest of the iceberg simply crumbling into an undetectable cloud of gas and a few icy grains. Perhaps most tantalizingly, the nitrogen iceberg model even offered a potential solution to the lingering mystery of its predecessor, Oumuamua. The greatest puzzle of that first interstellar visitor was its gentle acceleration away from the sun. A rocket-like push with no visible rocket engine. If Oumuamua was also a nitrogen iceberg, its outgassing would have been composed of pure nitrogen gas. This gas would be completely transparent, and if the fragment was dust-poor, it would create no visible coma. The result would be a very real physical push with no visible evidence of what was causing it. It would be a ghost rocket, perfectly explaining the observations without the need to invoke exotic theories or alien technology. While it can never be proven, the idea that both of the first two truly strange interstellar visitors were nitrogen icebergs from different parent stars provides a powerful and unified natural explanation for their bizarre behaviors. It suggests that interstellar space might be littered with these planetary shards, and that we have been visited by them not once, but twice. The story of 3I Atlas was no longer just about a single peculiar comet. It had become a story about the geology of alien worlds, a story that suggested the violent, planet-shaping processes of our own solar system are a common feature of star systems throughout the galaxy. The legacy of this fleeting visitor, therefore, extends far beyond the simple confirmation of a new class of celestial object. The true significance of 3I Atlas is that it marks the dawn of a new era in the exploration of the cosmos, the beginning of a field that might be called interstellar archaeology. For centuries, our study of worlds beyond our own has been an exercise in remote sensing, a science of shadows and ghosts. We have inferred the existence of exoplanets by watching for the subtle wobble they induce in their parent stars, or by detecting the minuscule dip in starlight as a planet passes in front of its sun. It is a science of profound ingenuity, but it is fundamentally indirect. We have been, like detectives, trying to understand a house by observing the flickering of its lights from a mile away. 3I Atlas and the interstellar objects that will follow represent something entirely new. They are the first physical artifacts from those distant, unseen houses to wash up on our shore. We can now, for the first time, study the actual stuff of other solar systems. It is akin to the difference between a historian reading a second-hand account of a lost city and an archaeologist holding a piece of pottery unearthed from its ruins. This single, fragile fragment of nitrogen ice carried with it a wealth of information about its birthplace. Its very existence provides powerful, tangible evidence that worlds like Pluto are not a unique quirk of our own solar system, but are likely a common outcome of planet formation throughout the galaxy. The theories that predict the formation of countless dwarf planets in the cold, outer regions of planetary systems now have a piece of physical evidence to support them. It tells us that the universe is probably filled with these small, geologically active worlds, their surfaces painted with glaciers of frozen nitrogen and methane. Furthermore, the fact that such a fragment could be created and ejected on an interstellar journey tells us something profound about the dynamics of its home system. The energy required to not only chip a piece off a planet, but to accelerate it beyond the gravitational grasp of its own star is immense. This points to a history of violence and chaos. It suggests that its home system, like our own, likely went through a tumultuous youth, a period of gravitational jostling where giant planets migrated, flinging smaller worlds into new orbits or out of the system entirely. The journey of 3I Atlas began in a cataclysm, a cosmic collision that is a normal, if terrifying, part of how planetary systems evolve. This messenger has also given us a completely new tool to probe the demographics of the galaxy. Our planet-finding techniques, like the Kepler Space Telescope's transit method, are inherently biased. They are exceptionally good at finding large, Jupiter-sized planets that orbit very close to their stars, but they struggle to find smaller, Earth-sized or Pluto-sized worlds, especially those in distant orbits. The study of interstellar objects provides a different, complementary sampling method. It is a form of celestial beachcombing. We cannot choose what arrives, but every object that does provides a clue about the vast, unseen ocean of planetary systems. We could never hope to directly image a Pluto-sized world orbiting another star with current technology, yet 3I Atlas proves these worlds exist and tells us what their surfaces are made of. It allows us to study the galactic population of small bodies, a population that is otherwise completely invisible to us. The discovery of 3 interstellar objects in just a few years, with surveys that are still in their relative infancy, strongly suggests that interstellar space is far from empty. These messengers are likely crossing through our solar system all the time, most too faint to be seen. But that is about to change. High in the Chilean Andes, on a mountain called Cerro Pachón, a new eye on the universe is nearing completion. The Vera C. Rubin Observatory is a marvel of modern engineering, designed to conduct a survey of the sky of unprecedented scale and speed. Its mirror is a colossal 8.4 meters, or nearly 28 feet, in diameter. And its camera is the largest ever built for astronomy, containing over 3.2 billion pixels. Every few nights, it will scan the entire visible southern sky, probing deeper and seeing fainter objects than any survey before it. When it begins its legacy survey of space and time, it is predicted to discover not one or two more interstellar visitors, but a steady stream of them, perhaps dozens every single year. The study of these objects will be transformed from a curiosity into a statistical science. We will be able to determine if nitrogen icebergs are common, or if rocky, inert objects like Oumuamua are the true rarity. We will build a library of the debris from other star systems. And as we prepare to see these visitors in greater numbers, humanity is also preparing to meet one of them. The European Space Agency is developing a mission called the Comet Interceptor. Its design is revolutionary. The spacecraft will be launched to a stable point in space, about 1.5 million kilometers, or just under 1 million miles, from Earth, where it will wait, dormant. It will be an ambush predator, waiting for astronomers on the ground to find the perfect target, a pristine long-period comet from our own Oort cloud, or, most excitingly, an interstellar object on a favorable trajectory. When the target is found, the spacecraft will awaken and begin a journey to intercept it, to fly directly through its coma and analyze its gas and dust up close. The legacy of 3I Atlas is that it has shown us that the story of the cosmos is not just written in the light of distant stars, but in the very substance of the messengers that travel between them. It was a fleeting ghost, a whisper that lasted only a few months, but it taught us that we no longer have to be content with just looking at the stars. We can now wait for the stars to come to us. This radical new understanding of 3I Atlas as a planetary shard has profound implications, echoing far beyond the study of a single transient object and forcing a recalibration of our most fundamental ideas about how planets form and evolve. That this story could even be told is a direct consequence of our own recent exploration of our solar system's farthest frontiers. Had 3I Atlas arrived just a decade earlier, the nitrogen iceberg hypothesis would have been dismissed as wild, unsubstantiated speculation. But in the year 2015, humanity's robotic emissary, the New Horizons spacecraft, performed a breathtaking flyby of Pluto, transforming it from a distant, fuzzy point of light into a vibrant and stunningly complex world. The images it sent back across nearly 5 billion kilometers, or 3 billion miles, of space were a revelation. They showed a world with a vast, heart-shaped basin of frozen nitrogen, a glacier named Sputnik Planitia that stretches for over 1,000 kilometers, or more than 600 miles. This feature is not a dead, static ice field. It shows clear evidence of convection, of slow, churning currents of nitrogen ice flowing like a thick fluid, constantly renewing its surface and erasing impact craters. We saw mountains made of water ice, as hard as granite at those cryogenic temperatures, soaring to heights of several thousand meters, or over 10,000 feet, their peaks dusted with methane snow. We saw evidence of possible cryovolcanoes, which would have erupted not with molten rock, but with a frigid slurry of water, ammonia, and other ices from the planet's interior. New Horizons proved that a small, distant world, heated only by the faint embers of its own radioactive core, could be a place of active, dynamic geology. This detailed, intimate knowledge of Pluto provided the crucial ground truth, the real-world example that made the theory about 3I Atlas not just plausible, but probable. We were not inventing a new kind of object from whole cloth. We were simply recognizing a familiar face in a crowd of strangers. The legacy of 3I Atlas is therefore inextricably tied to the legacy of the New Horizons mission. Together, they tell a consistent story. The processes that shaped Pluto are not unique. Star systems across our galaxy are likely churning out these small, volatile-rich worlds in their billions. They are a standard, common product of planet formation. This provides a powerful piece of physical evidence for our theories. Our computer models have long predicted that the outer edges of nascent solar systems should be vast nurseries for such dwarf planets. But a model is only a prediction. 3I Atlas is a physical sample, a data point delivered directly to our doorstep from an alien laboratory, confirming that our understanding is on the right track. It carries the message that the galaxy is filled with countless Plutos, each one a potential storehouse of the complex organic molecules that are the precursors to life. This realization also forces us to broaden our definition of a potentially habitable world. For decades, the search for life beyond Earth has been dominated by the concept of the Goldilocks zone, the narrow orbital band around a star where temperatures are just right for liquid water to exist on a rocky planet's surface. But the active geology of Pluto, powered by internal heat, hints at another possibility. Many planetary scientists now believe that Pluto may harbor a vast ocean of liquid water deep beneath its icy shell, kept from freezing by the slow decay of radioactive elements in its core and insulated by the thick crust of water ice and frozen nitrogen above. If such a subsurface ocean can exist on Pluto, then similar oceans could exist on the countless exoplutos that are likely scattered throughout the galaxy. These worlds would be habitable in a completely different way, their potential for life entirely independent of the light and warmth of their parent star. 3. Atlas, as a fragment of such a world, is a messenger from this vast, hidden realm of cosmic possibility. It tells us that the ingredients for life and potentially habitable environments may not be confined to the temperate, sunlit garden worlds, but may also be found in the cold, perpetual twilight of deep space. Finally, the very journey of this object speaks to the violent and interconnected nature of the galaxy. For a piece of a planet to be ejected into interstellar space, its home system must have experienced a powerful gravitational disturbance, likely from the migration of giant Jupiter-like planets early in its history. This aligns with modern theories about our own solar system's evolution, which propose that Jupiter and Saturn went on a chaotic journey, a grand tack that flung debris everywhere, shaping the asteroid belt and seeding the outer solar system. 3I Atlas is a piece of shrapnel from just such a celestial billiard game, a game that plays out in star systems across the Milky Way. It shows that star systems are not isolated islands. They are leaky, constantly exchanging material with their neighbors over millions of years. This raises the tantalizing, though highly speculative, possibility of panspermia, the transfer of life, or the chemical precursors of life from one world to another, and even from one star system to another. An object like 3I Atlas, a nitrogen iceberg, offers a perfect vehicle for such a transfer. Any microbial life or complex organic molecules trapped within it would be in a state of perfect cryopreservation during its long, cold journey through the void. We have no evidence that this object carried any such passengers, but its existence proves that the transportation mechanism is real. The galaxy has a delivery service, and the packages are pieces of other worlds. This fleeting messenger, which survived for eons in the dark, only to perish in the light of our sun, has left us with a legacy of profound insight, forever changing our view of the galaxy from a collection of isolated points of light to a dynamic, interconnected ecosystem of worlds. And so, our understanding of the cosmos has been irrevocably altered. The story of 3I Atlas is a perfect microcosm of the scientific process itself, a journey that began with a single, ambiguous point of light and ended with a profound new insight into our place in the galaxy. We have followed this faint, anonymous traveler from its discovery by the tireless, robotic eyes of the Asteroid Terrestrial Impact Last Alert System to its ultimate fiery demise. We saw how it initially defied our neat classifications, a ghost of a comet that produced a faint, puzzling coma, a whisper of activity that hinted at a composition unlike anything native to our own solar system. It was a riddle, wrapped in the cold vacuum of space, its dramatic disintegration, a spectacle of self-destruction that played out across hundreds of millions of kilometers or hundreds of millions of miles, was not an ending, but a revelation. In its ashes, we found a stunningly simple truth. This was no primordial comet forged in the nebula that birthed our sun, but a fragment of a distant world, a nitrogen iceberg calved from the surface of an alien Pluto. This elegant hypothesis, born from our own recent exploration of the Kuiper Belt, transformed every piece of strange evidence into a coherent and compelling narrative. It joined Oumuamua and Borisov in a new, exclusive catalog of interstellar visitors, each one a unique messenger, carrying its own set of clues from an unknown shore. But this is only the beginning. For centuries, our discovery of these travelers has been a matter of pure serendipity, a cosmic lottery. Now, we stand on the cusp of a new age of discovery. With the advent of new sentinels, like the Vera C. Rubin Observatory, with its vast mirror measuring 8.4 meters, or nearly 28 feet across, our ability to scan the heavens is about to take a quantum leap forward. We will move from finding these objects once every few years to potentially detecting a steady stream, transforming the study of interstellar messengers from a novelty into a new, vibrant branch of astronomy. Each new visitor will be a postcard from an unknown star, another piece of the grand puzzle of how planetary systems form and evolve throughout the cosmos. We look to the heavens now, not just with wonder, but with a new sense of anticipation, knowing that the void is not empty, but filled with the secrets of a million worlds, waiting to be discovered, one messenger at a time.